All right, guys, so we are going to now, after getting into balancing equations, talk about classifying reactions. And we have five main types. We're going to start with combustion, which is actually probably the simplest, although they can be tricky to balance. So the definition is simply any time a hydrocarbon, which is just carbon, hydrogen, and sometimes oxygen, reacts with oxygen, O2, it's going to give us CO2 and H2O every time. This one is the easiest reaction type to predict the products of because it always gives you CO2 and H2O, period. If you have a hydrocarbon, in other words, C, C anything, H anything, and then you have oxygen, it's always going to give you CO2 and H2O. All right, it's very exothermic, and the big reason for that is that the CO2 and H2O that we're making are really low in energy. So their bonds are very stable, and so in order to form those bonds, we release a lot of energy. And so that's where what you normally think of with combustion, fire, heat, light, that's where that comes from. So these are always going to be very exothermic. So let's flip the page over, or actually move on to the rest of the packet that hopefully you picked up. Combustion examples. Let's just go through a couple of examples. We're going to start with very, very simple, and we'll demonstrate this one in class next time. CH4 plus O2, this is just methane. Oops, started to predict the products for you. CH4 plus O2, so just methane and oxygen. And that methane is, well, you could call it carbon tetrahydride if you named it according to the binary system that I gave you in the last unit. And so it's a hydrocarbon. It contains only carbon and hydrogen. It's reacting with pure oxygen. And so we know every single time, without really doing any thinking or analysis, it's going to give us carbon dioxide and it's going to give us water. And so the only thing we have to be mindful of is to remember to balance. Okay. So right now we've got one carbon on each side. We've got two hydrogens on the right and 4 on the left. So I'm probably going to want to multiply that water by 2, right? And that also gives me, if we count it in both places, we have 2 oxygens there and then another 2 oxygens there, because we have to multiply the coefficient, which is of course the big number out in front, by the subscript, which is an implied 1 for oxygen. So we have 2 oxygens there as well as 2 oxygens in that CO2 molecule. So that's 4 oxygens. So now I'm just going to go ahead and put a 2 in front of O2 because, of course, if I multiply coefficient by subscript, I get 4. All right, let's try another one. Let's go with C5H12 plus O2. And we know it's a hydrocarbon because it's just carbon and hydrogen, and it's reacting with oxygen. So, of course, what products are we going to get? Not really a whole lot to do in terms of prediction. It's just going to be CO2 and H2O every time if it's combustion. Okay. By the way, I should say something about physical states here. Both of our products are going to be gases, and that's simply because of the heat involved. So you might be thinking, well, wait a minute, when I burn, when I burn something, I don't see drops of water. I don't see liquid water. Well, that's because, of course, the heat involved in the reaction is going to turn any water into a gas, or at least keep it a gas as it's formed. Okay, the key here, guys, with these combustion problems is we want to balance oxygen last. And the reason we do that is because oxygen is by itself, and anything I put in front of that O2 on the left is not going to affect any carbon or hydrogen. So if we go through this, maybe I choose to balance carbon first. Okay, so that means I'm probably going to have to put a 5 out in front, right? All right, and so let's go over to, and I did just change my oxygens by adding that 5 as well, but let's, again, save oxygen for last, and let's go over to hydrogen. I have 12 on the left, right? And I have 2 on the I have 12 on the left and 2 on the right. So I need to multiply that H2O by 6, right? And that will give me 12 hydrogens on both sides. The last step, of course, is to take care of the oxygens. So I've got 5 times 2, and of course that's 10. And then I've got 6 times 1, so that's 6. And if I put them together, I have 16. So over here on the left, I want to say, okay, 2 times what will give me 16? And of course, that number is going to be 8. Okay, so there's my balanced equation. All right, let's try another one. Let's go with C4H10. And of course, I'm not even, normally if we were predicting other reaction types, I would pause and say, okay, what's this going to give us? Well, it's going to give us the same thing every time, right? So it's going to give us CO2 and H2O. All right, and then, so again, we want to save oxygen for last. So that means we're probably going to want to put a 4 in front of carbon dioxide to balance our carbons. And then what will we put in front of water? All right, well, we have 10 hydrogens on the left, so I need to multiply my water by 5 to get 10 hydrogens on the right. So 5 times 2. Okay. All right, now this one, the oxygens are a little bit strange. I've got 4 times 2 is 8 plus 5 times 1, of course, is 5. So that gives me an odd number, it gives me 13. All right. So if I have 13 on the right, 2 times what gives me 13? Well, of course, that's a decimal or a fraction. That's 6.5. But we can't have 6.5 oxygen molecules, right? So we can't really leave that coefficient there. Otherwise, that would stand for 6.5 oxygen molecules, and that doesn't make sense. It has to be a whole number, right? So the only thing to do now at this point is if we go ahead and double that 6.5, that's going to give us the whole number 13. And I can do that as long as I do go ahead and double everything else as well. Okay, so for example, if 6.5 is going to become 13, that means 1 has to become 2. So I put a 2 out in front of the C4H10. The 4 becomes 8, and the 5, of course, becomes 10. And there we go, we're all balanced. And of course, even though everything has a coefficient, it can't be reduced because we got that 13 in there. Okay, let's try one more. This time we're going to have C2H5OH plus oxygen. Now this one looks a little bit different because our hydrocarbon also has oxygen in it, but it doesn't change the fact that this is combustion of a hydrocarbon, and so it's going to give us the same products. Okay, so CO2 plus H2O. All right, and so we're going to follow the same logic we've been following. We're going to save oxygen for last. So if I start with carbon, that means I'm going to put a 2 in front of CO2 to give me 2 carbons on each side. And then hydrogen, it looks like I have to remember to count up both of these. So 5 plus 1 is 6 hydrogens on the left. So I'm going to multiply this water by 3. Okay. And then my oxygens, so on the right I have 2 times 2 is 4, plus 3 times 1 is 3, and that's going to give me 7. Now, it actually works out pretty well this time because even though it's an odd number, I have this sort of extra oxygen on the left that's by itself. And so if I think of that as being my 7th oxygen, okay, then I just need 6 more from the O2. So what times 2 would give me 6? So hopefully you would say 3 there, right? And so if you see what I mean here, 3 times 2 is 6 plus this 1 oxygen on this other 1 oxygen on the left that gives me 7, and that matches the 7 that I have on the right. So it's really not so bad when we have that oxygen showing up in 2 places. All right, so go ahead and give the assignment a shot. Try to predict imbalance and see how you do.